From the smallest atom to the largest galaxy, everything in the universe is affected by gravity. This invisible force shapes our world in ways we often take for granted. But have you ever stopped to wonder what exactly is gravity, and why do we fall down when we jump? Join us as we explore the fascinating science behind this universal phenomenon that keeps us grounded literally. How does gravity work? The answer may seem simple enough. It's the force that pulls us towards the ground and keeps our feet firmly planted on the earth. But the truth is far more intricate and mind-boggling than that. So buckle up and get ready for a journey into the heart of one of nature's greatest mysteries. The gravity puzzle. Why do we fall? As children, we experience the world through our senses. We see objects around us and assume they're always going to be there. But have you ever stopped to think about why the chair you're sitting on doesn't fall to the floor, or why the earth itself doesn't collapse in on itself? Enter gravity, the invisible force that holds our world together. Without gravity, our planet would quite literally fall apart. But what exactly is gravity and how does it work? To understand the science behind this phenomenon, let's start with something we all know well: magnets. Magnets have an invisible force that attracts certain materials like iron. This force is strongest at the poles, where the magnetic field lines are most concentrated. Similarly, the Earth has a gravitational field that extends from its core to the farthest reaches of space. This field is created by the planet's mass, which is concentrated at its center. As you move closer to the Earth, the gravitational field becomes stronger, pulling you towards the ground. That's why when you jump, you come back down. Gravity is constantly pulling you back to the surface of the Earth. But why do we fall down specifically? To answer that question, we need to look at the structure of the atom. Everything in the universe is made up of tiny particles called atoms. Atoms have a central nucleus surrounded by electrons that move in specific paths. When two atoms come close together, their electron clouds can interact, creating a force of attraction or repulsion. If the force of attraction is stronger, the atoms will form a bond and stay together. For example, when you walk on the ground, your feet are really just different types of atoms coming together and sticking due to the force of gravity. Unraveling gravity. From Newton to Einstein and beyond, understanding the true nature of gravity has been one of humanity's greatest scientific challenges. From the time of ancient Greek philosophers to the modern day, countless minds have pondered this elusive force that binds us to the earth and governs the motion of celestial bodies. Sir Isaac Newton, the legendary physicist and mathematician, who lived from 1643 to 1727, made significant strides in understanding gravity. He developed his law of universal gravitation, which states that every particle in the universe attracts every other particle with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. This groundbreaking work laid the foundation for our understanding of gravity and its effects on the physical world. However, as scientific knowledge advanced, some anomalies in Newton's theory came to light. Enter Albert Einstein, the father of modern physics. Einstein's theory of general relativity, published in 1915, revolutionized our understanding of gravity. He proposed that gravity is not a force, but rather a curvature in the fabric of space-time, caused by the presence of mass and energy. This mind-bending concept turned the way we perceive the universe on its head and paved the way for new discoveries in cosmology and astrophysics. Despite the incredible progress made by these brilliant minds, the true nature of gravity remains a profound mystery. Scientists continue to grapple with its complexities, seeking to unravel its secrets and develop a more complete understanding of this fundamental force. From the subatomic realm to the vast expanse of the cosmos, gravity's influence is undeniable. Gravity Explained, the invisible hand of the cosmos. Have you ever reached out to touch something only to miss because it vanished before your fingertips could make contact? Welcome to the perplexing world of quantum mechanics, where the very nature of reality is called into question. and the laws of classical physics no longer apply. At the quantum level, particles exhibit wave-like properties and can be in multiple states at once. This phenomenon, known as superposition, allows particles to exist in a realm where they are both here and there simultaneously. But as we attempt to measure or observe these particles, they seemingly collapse into a single state, giving us a definite position or momentum. This active observation becomes a pivotal moment, altering the very essence of the particle and bringing it into the tangible realm of our perception. Imagine you're standing on a tightrope walking between two buildings. The tightrope represents the delicate balance between order and chaos, stability and uncertainty that governs our universe. As you take each step, you must carefully consider your next move, aware that a misstep could send you plummeting to the ground below. In this precarious situation, you find yourself suspended between the known and the unknown, much like the particles in our quantum realm. But what happens when the tightrope snaps? The very fabric of our universe is thrown into disarray, leaving us to navigate a world where nothing is certain and everything is in flux. This moment of instability gives rise to the enigmatic force of gravity. Gravity emerges as a stabilizing force, pulling us back to the safety of the known, anchoring us to the familiar ground of classical physics. Is gravity a force or an illusion? Discover the truth. What if I told you that gravity might not be a real force, but just an illusion? Sounds crazy, right? Well, stay tuned and let me explain. As we've discussed earlier, Sir Isaac Newton developed his law of universal gravitation, which explains how every object in the universe attracts every other object with a force that depends on their masses and the distance between them. This has been the prevailing theory since Newton's time. However, Albert Einstein turned that around with his theory of general relativity. He proposed that gravity is not a force, but rather a curvature in spacetime, caused by the presence of mass and energy. According to this theory, objects don't attract each other. They simply move along the curves in spacetime created by the mass of other objects. This may seem like a subtle distinction, but it has profound implications for our understanding of the universe. If gravity is not a force, then what is it? Well, according to Einstein, it's a geometric property of spacetime. Spacetime tells matter how to move, and matter tells spacetime how to curve. This means that gravity is not a force acting at a distance like we often think of it. Instead, it's a response of objects to the curvature of spacetime around them. So is gravity an illusion? Well, it depends on your perspective. If you're used to thinking of gravity as a force, then Einstein's theory may seem counterintuitive and even mind-bending. However, if you embrace the idea that gravity is just a property of spacetime, then it makes perfect sense. Ultimately, the truth lies somewhere between these two perspectives. Gravity is both a force and an illusion. It's a force in the sense that it causes objects to accelerate, but it's also an illusion because it's not a real force acting at a distance. Rather, it's a response to the curvature of spacetime. If you want to learn more about the fascinating world of gravity and other mind-blowing concepts in physics, make sure to subscribe to our channel. We explore the latest discoveries and research in physics, cosmology, and other scientific fields.